Hey, this is homework set number 5 for ECE 341. This covers geometric and Pascal distributions. And actually, this is really more Pascal distributions. The first problem looks at how to combine two geometric distributions. The first one is the number of times you have to roll a 10-sided die until you get a 1. And B is the number of times you have to roll a 10-sided die until you get a 1 or a 2. So these are both geometric distributions. The first has a probability of 1/10. The second has a probability of 1/5. So doing that, let's have k go between 0 and 50. P is 1/10. So the PDF of a geometric distribution is P times q to the k minus 1. Or, yeah, that's right. And the first point is 0 because it takes at least one toss to get a heads, get a 1. So this is what the PDF looks like. And notice that at 0, there's no bars. The bar starts at 1, then decays exponentially. I took it out to 50. The average is 1 over p, or 10. So taking it out to 50, it's not quite at 0. It's going to lose a little bit of error, a little bit of inaccuracy. It's better if you take it up further, say to 100, but I went to 50. For B, again, this is a geometric distribution with a mean of 5, or probability of 1/5. So doing the same thing, P times q to the k minus 1. The first point has to be 0. Here's the bar chart. The PDF of A plus B is actually convolution. It's the convolution of A and B. So if I plot that as a bar chart, it takes, this is going to be 0. Come on, guy, draw. There we go. I go 0, 0. So this I've got 0, 1, 2. It takes at least 2 tosses to have a chance of getting a 1 on the first roll, then 1 or 2 on the second roll. And the likelihood increases, then tapers off. Again, going out to infinity. And looking at k versus the p of k, again, it takes at least 2 tosses to get a result. Now that number is actually just the two p's multiplied together. 0.1 times whatever that is, 1/5. Problem 2 looks at solve the same problem but using z-transforms. Now this is where the z-transforms really shine, is with exponential distributions. The z-transform of a geometric is p over z minus q. That's for A and B. Put the two together, that's just the product of the z-transforms. Convolution in the time domain becomes multiplication in the z domain. That's why we like z-transforms. So that's the z-transform of C. To find the inverse z-transform, here's a trick. There's a couple ways to do it. If I make the numerator the same order as the denominator, there's no delay. So let's multiply both sides by z squared. I'll keep one of the z's outside because I'll need that later. Now do the partial fraction expansion of this. Expanding over the 0.9 term, I cover up the 0.9, analyze the 0.9 and get 0.18. Then to find the 0.8 term, I cover up the 0.8, plug in z equals 0.8, and I get 0.16, minus 0.16. So there's the partial fraction expansion. Multiply through by z, and I can find this term and that term. So this is 0.18 times 0.9 to the k, minus 0.16 times 0.8 to the k. Now divide by z squared, that means delay everything by 2. So k goes to k minus 2 everywhere, and there's your z-transform, or the PDF for C. And there's a couple of other ways to write it. I could take this minus 2 and have 0.18 divided by 0.9 squared. Your pick. This is one form. There's other ways to write it. As a check, if I plug in C of 5, I get 0.0493, which matches up with what I got with convolution. That's problem 2. Problem 3 is roll a 6-sided die till I get a 1, then roll an 8-sided die till I get a 1, then roll a 10-sided die till I get a 1, how many times did I have to roll the dice? What's the PDF of that? Well, problem 3 says solve using convolution. In this case, I'm going to go out to 100. Again, the mean is 6, 8, or 10. Just to be safe, I'll go out 10 times further. For A, P is 1/6. For B, P is 1/8. For C, P is 1/10. Convolve A and B. Convolve that with C. And there's your PDF. And if I do a bar chart, that's what it looks like. And the numbers, again, I'm going to get no results until I get to 3. It takes at least 3 coin tosses to get 3 successes. Problem 4 is solve using Z-transforms. So again, this is the PDF of A, or the Z-transform of A, Z-transform of B, Z-transform of C, or in statistics, we call that the moment generating function of A, moment generating function of B. Pick your name. In electrical engineering, we call it Z-transforms. D will just be the product of the Z-transforms. So again, doing the trick, this is a third order denominator, so let's multiply by Z cubed to make it a third order numerator. Keep one of the Z's outside, do the partial fraction at the inside. Again, to get the 5/6 term, I cover up the 5/6, plug in Z as 5/6 everywhere, and I get 0.5208. Likewise for the other terms. Multiply through by Z, I can now take the inverse Z transform. This is 0.5208 times 5/6 to the k, minus 1.53 times 7/8 to the k, 1.01 times 9/10 to the k. Now divide by Z cubed, which means delay everything by 3. Also all the k's go to k minus 3. And there's the the PDF for the convolution of A, B, and C, or the number of die rolls it's going to take until I get a 1 with a 6-sided die, 8-sided die, and 10-sided die. As a check, if I plug in at 8, I got 0.0218 using convolution. Plug in 8 into here, I get 0.0218 using Z-transforms. Looks like the right answer. So that's homework set number 5 for ECE 341.